Thanks for the introduction. So touchscreen watches are more and more common, but if you look at the standard interaction techniques on these devices, you see a lot of this. You have coarse directional swipes through screens with only one or just a few buttons. And I counted, and to select an album on the Android Music app required 4 swipes and 2 taps just to get to the list of items, and then you'd have to do more interactions from there. So this is really slow, and it defeats the point of smartwatches, which is to have these really fast interactions while you're doing other things. I mean, these devices, they're competing with taking a smartphone out of your pocket in a lot of cases, so interactions have to be really, really fast. So in this work, we're interested in exploring higher bandwidth input for touchscreen watches, and specifically, we're interested in the question, can spatial menus enable rapid command selection on touchscreen watches? And for those of you who aren't familiar, in a spatial menu, commands are associated with spatial locations and then executed by indicating a spatial location to the system. So here's an example of a spatial menu for tablets called FastTap. The menu has a novice mode where you touch a menu button with one finger to open the menu and then use another finger to select the item. But then over time, you build up a spatial memory for where the items are, and then you can rapidly select items with a 2-finger tap, and you'll see that in a second here. So you see some selections there that are more rapid. So these menus are like keyboard shortcuts for touchscreens, and they're extremely fast. So we wanted to see, could we apply this approach to touchscreen watches? But it really wasn't obvious if this would work because these devices have such a small input space. So overall, there's just not a lot of area to interact with. And also, multitouch becomes more challenging because you have occlusion and fingers being super close together. So I'll kind of just spoil the talk right now and say that we found that spatial menus can be adapted to work on tiny touch screens. They enable fast selections, about 1 second per selection with practice. They can support up to 18 commands at that speed, showing using a design that I'll show. They can be learned quickly, and they have relatively low error rates. But let me just step back for a second. To get to these findings, we looked at 2 execution mechanisms, which I'll show you in a second. We investigated the impact of button size on performance and accuracy. We looked at this idea of overloading locations to accommodate additional commands that I'll describe. And then we evaluated our techniques against the status quo. So I'll just kind of go through these in turn. So the first execution mechanism we looked at was just a straightforward application of the FastTap menu that I showed earlier to a watch screen. You have this kind of novice mode where one finger opens the menu and then the other selects an item. But then once you've built up some spatial memory, you can do an expert mode where you just tap the 2 simultaneously. And then the second technique, TwoTap, is similar, but it uses 2 sequential taps to achieve about the same thing. So in a novice mode, you tap visual search and then tap a target item. Just one more time. But then once you know the item locations, you can do 2 taps quickly without a visual search. And one of the hypotheses that we had in this work was that over time, these 2 actions would become integrated into a single kind of chunked motor action, similar to how when you unlock a lock screen on your phone, you don't think about hitting each of the individual buttons. You just kind of perform the whole thing. So next, we conducted a study to understand basically how many locations we could fit on one of these tiny screens. We looked at 3 grid sizes shown here. And for each grid size, we had participants perform sets of trials simulating the 2 WristTap interaction techniques. So here's what that looked like. This is simulating the fast selection. Again, the fast selection on a 4x4 grid. And then this is the novice selection on a 3x3. So we had 14 participants. And each of them performed trials for each grid size and selection method. In terms of performance, we found a significant main effect of both the grid size and the selection method. The 2-step novice selections took between 1.2 and 1.4 seconds, and the 1-step expert selections were between 600 and 800 milliseconds. But the key thing here is error rate. For error rate, both the 2x2 and the 3x3 grids had a median of 0 errors, and both had averages that were under 1%, so that's quite good. But then the rate of errors was higher for the 4x4 grid. So based on these results, we decided to go with 3x3 grid because it has a near 0 error rate and comparable performance to the 2x2, but it can fit more items. But with a 3x3 grid, that would mean we could only support 8 commands. You've got 9 spots, and you need one for the menu button. So to enable more commands, we investigated the idea of overloading grid locations. So to accomplish this, we have multiple menu buttons, each with their own set of commands. So you have the 3 menu buttons along the bottom there. But this kind of raises this question. How does the overloading of menus impact people's ability to adopt this expert selection technique? Remember, these techniques, they really only get fast once people build up the spatial memory and can perform them without the visual search. So we want to make sure that this could still be done when we've got these 3 overlapping menus. So to test this, we had participants perform trials where they were asked to select prompted items. So there's a one-step selection. This is what it looked like. And we selected a subset of the items in these 3 menus so that for some grid locations, the participants only needed to learn 1 item, but for others, they had to learn 2 overlapping ones or, and then in one position, 3 overlapping items. And the study had 3 training stages where we encouraged participants to try and learn the item locations, followed by a testing phase where we asked them to just use the expert technique exclusively, even if they weren't fully confident in using it yet. So here's the rate of use of the fast expert selection technique over time. We can see that in less than about 20 minutes, that was the duration of the study, participants went up to about 80% usage of the expert technique. And then you can see in the testing phase, it was near 100%, but that was because we explicitly asked them to use it there. For that final testing stage, in terms of performance, the average trial time when there's no overlap, where you're only learning 1 item at a location, was faster, but not significantly so. And in terms of accuracy, overall, we saw a median error rate of 3.6% for users. But we really observed a high variation in error rates across users. About half of the users had error rates of less than 2%, many of them with 0, and then the other half were quite a bit higher in the 4% to 10% range. We also looked at it breaking down by the number of overlaps, and we found greater error rates with more overlapping items. So overall, at the end of the day, what this suggests is that overloading does slow down learning somewhat, but users can learn overloaded menus and use them quickly and accurately. And in 20 minutes, they're able to learn half of the 18 menus or 18 items in the 3 menus. So finally, we tested our techniques against existing methods. For this study, we had participants perform the trials while standing. The watch would buzz, and then they would raise their arm, do a short block of trials, and then they'd lower their arm again and wait for the next block. And we had a video playing of a walking tour of Amsterdam, and that was just to simulate just some distractions in the environment. We had 3 conditions. Here's the WristTap condition. Here we didn't have the swiping through targets. You just had to select them to complete it. Here's the TwoTap condition. You've seen these before. But finally, we had this swipe and tap condition, and this was designed to simulate the interaction techniques that we see in many of the current smartwatch apps. You have something where you open a menu, and then you have this vertical list of things that you swipe through and then select from. Each of our participants experienced all 3 of the menu systems. This is a within participants design. And for each menu system, there was a training phase and then a testing phase where we were gathering data. So what did we find? Well, here's the error-free trial completion times for the testing stage by technique. And we see that the WristTap selections took just under a second to perform. The TwoTap took about a second, and swipe and tap was more than double the time at 2.6 seconds per selection. And a repeated measures ANOVA found that WristTap and TwoTap were each faster than swipe and tap, but there was no significant difference between the two techniques. In terms of error rates, we did an analysis for both selection errors, where an incorrect item was selected, but also for category errors, where the participant opened the wrong menu, but then they could still recover from them. And we can see that WristTap and TwoTap both have higher error rates than the control condition swipe and tap, but these errors are still pretty low, around 3% or lower. WristTap had more selection errors, which makes sense because the fast selections in WristTap were performed in one action, so there's no way to recover once you've started the action. TwoTap, on the other hand, had more category errors but fewer selection errors. And that actually conversely suggests that with TwoTap, people can recover once they open up the incorrect menu. So both of our techniques were faster than the status quo, but they kind of each have distinct characteristics that are worth highlighting. So first, WristTap's expert mode, because it uses multitouch to do selections, it can kind of coexist pretty well with the interaction methods that we commonly already see on watches. So it could be applied in an existing app as kind of a shortcut method without too much modification. Second, WristTap had the disadvantage of higher selection errors, which would suggest that it should be used in scenarios where an error has a low impact or could be quickly reversed. So I kind of think of it as, you could imagine a quick gesture to put my phone into airplane mode or something like that. If there's an error there, it doesn't really matter, but it would be a very fast interaction. And finally, it was slightly faster than TwoTap, though, like I said, in our study, we did not find a significant difference there. TwoTap, on the other hand, is conceptually simpler. It's only one selection method. You don't have this difference between open, touch, and two fingers together. It also has the lower selection error rate because these category errors are recoverable. And it also could conceivably support more menu items than WristTap, because you don't have to have a dedicated grid location for the menu button. You could have grid locations for both menu buttons and then items once they're tapped. And there's more information on that in the paper in case you're interested. So I'll just end with some takeaways. Spatial menus can work on tiny touch screens. Overloading 3x3 menus we found to have a minimal impact on adopting the expert selection technique. They're significantly faster than standard techniques with low error rates, and they have different comparative pros and cons, which I've discussed briefly. So with that, I'll finish, and I'd be happy to take questions. Thank you.
Did you consider using or testing gestures or swiping as the ones you see in some novel keyboards for smartphones?
Like swiping between different grid locations to do something? Mm-hmm. We didn't look at that, but that is kind of interesting. I have seen some text entry methods that, even for watches, that use that kind of swiping approach, but we didn't look at it for doing command selection, not in this work.
Can I ask just?
Oh, please, yeah.
Why do you think that the TwoTap has the category errors?
It's a good question. I'm actually not quite sure on that. I'm not sure why it had a higher error rate for the category errors. I was going to say it could be just the difficulty of targeting the items in the 3x3 grid, but our first study, we looked at that, and the error rate was like less than 1%. So it's a very good question, and I'll think about that, I guess.
And do you think this will still work when we use it on the lab?
Yeah. I'm not sure. We're really kind of interested in. Well, for the first two studies, they were performed sitting down, and so in this third study, we're like, okay, we have to do something that's a little bit more like you're on the go, you're doing something, and so we did this standing up. We didn't go as far as to get a bike or something like that, but it is really a good question. One thing that we did do in the paper that I didn't talk about for time is we had a block at the end of the third study where we blanked out the entire screen and said, now do the selections. You saw the stimulus, but you didn't see the menu items at all. And for both of our techniques, people could get 80% accuracy with absolutely no visual feedback whatsoever. And we didn't test it for the control condition because that just would not work because it relies so much on visual feedback. So that might bode a little bit well for doing it while riding a bike, but I'm not. There's still shaking and other stuff there, but it's a good question.
Okay, any other questions? Okay, thanks very much, guys.
Thank you.